So good morning, I'm Bill Langdon. This is a talk on using genetic improvement to improve genetic programming. This is work that we published in the CEC 2020 conference. Before I start, I'd like to explain in the slides, if you get these from my homepage, you see on the slides various parts are underlined in blue. Those are hyperlinks to papers and code and so on. So, genetic improvement of genetic programming. What we've done is to apply genetic improvement to what was at the time the fastest GP system on the planet. It got its speed essentially from multiple levels of parallelism, in particular the use of Intel AVX parallel vector instructions, which allowed its CPU to perform 16 floating point operations in parallel. GPavx is actually built on top of Andy Singleton's GPquick. And what we showed last year at the A-Life conference was GPavx can evolve trees of hundreds of millions of code. The downside of that is, of course, it takes a long time, literally days to run to that length. And most of the overhead is still in the AVX interpreter, despite the parallelism. So we wanted to see, can genetic improvement on the interpreter give us a better GP system? The target system is the same as we used in the A-Life paper. It's the Coase's sextet polynomial. We're going to run without a size limit. Run for up to 1 million generations, and as you would expect, over that length of time, the trees bloat to enormous size. So this is our target that we actually want to produce a better interpreter for. The sextet polynomial is a smooth curve, but the task is actually to match those 48 points chosen at random along the curve. The GPquick EVAL is essentially a recursive operation. So for binary functions, we call eval twice, evaluate their return values, and return the product, the sum of their two values. In the case of leaves, we simply return the value. Notice that this uses the system stack, and the tree must be evaluated once per fitness case. The other thing that GPquick does is it flattens the tree into a very tight linear string, so this enables us to store huge populations. The trees actually evaluate to 255 opcodes, and those opcodes are used as index into a table of functions, and the eval actually calls those functions according to the opcode. In the case of GPX, the way that we interpret the opcode is we have a new macro which, instead of evaluating one floating point value, actually evaluates all 48 test cases. So instead of passing through the tree 48 times, the GPX interpreter just passes the tree once. And for each node within the tree, it operates on an external explicit stack. So our eval takes data from the top of the stack and leaves answers on the stack. In terms of the CEC 2020 paper, it has a lot of experiments. What we're going to do is concentrate on the last one, in which we evolve the complete GPavx interpreter. We will target specifically trees of about 20 million nodes, and what we're going to show is the mutant that we produce at the end of this generalizes well on trees from size 3 to 100 million nodes. We use the usual GI approach of converting the C++ code into a grammar. We then can apply mutation and crossover to the grammar and evolve it. The fitness function is essentially, does the mutant compile? Does it run without error? Does it return the right values? We test it on random trees, which we change every generation. And each time we run eval, we compare the values it returns with the original code and require all 48 answers to be identical. The second comparison is in terms of the runtime. Did the mutant code run faster or slower than the original? And then we select the better half of the population to be parents for the next generation. So our fitness function is very much based on wall clock time. So this is running on a multi-user AVX server. The load varies according to who else is using the server at the same time. The server can actually change its own clock frequency. The operating system can move us between cores and so on. So this is a very noisy environment. In order to combat the noise, what we actually do is run the performance of the original code and then of the new code. So we're always doing a comparison between the original and the new code, and we run those as tightly together as possible. In the case of small trees, the code is usually run on the same core at the same frequency. So we run a set of 11 pairs of runs, and the difference is the first quartile time. So what we do is effectively to divide the 11 runs in half, discard the slower half, and then use the average of the first half. So this gives us a very robust average. Only in the case of larger trees do we run just once. Larger trees typically take of the order of a second to run, and so the noise is proportionately less, and we only need to run the one time. We're actually going to do 6 different types of experiments. The first option we give the GI system is we do a comparison between new code written using a switch statement versus the original GPquick system of having the jump table. The second one is to have an internal stack versus the external stack. So in the internal stack, each eval actually returns a vector of floating point numbers, whereas in the external stack, remember, the values are left on the stack. If we're running with the internal system stack, then we can either return 16 test cases together, or we can return all 48. So if we return 16, then we have to process the tree 3 times in total, whereas if we return 48, then the tree is, as usual, evaluated in a single pass. For each of those 6 options, we generate grammar. In addition to the grammar, the GI system has access to the whole of the Intel intrinsics library. Most of the grammar rules are simple line operations, so we can do things like delete lines of code, move lines of code around, insert copies of lines of code, and so on. And we're going to concentrate on the option with the switch and the explicit stack, as this was the most successful of all 6. Nevertheless, of the 6 runs, they all ran successfully. Population of 100 and 100 generations approximately runs overnight. And here what we've on this graph, what we're showing is the evolution of the population over time. So time is running left to right, and the different ways in which mutants can fail is running into the paper, and on the vertical scale we have the number of individuals within the population. So remember, we have a total of 100 individuals in each population. If we look at generation 0, we can see that approximately 50% of our mutants fail to compile in the initial generation, but over the first 6 or so generations, this falls to approximately a quarter. So approximately a quarter of our mutants fail to compile. If we look at so this graph is looking at summing up all 101 generations, what we see is as again about 27% of the mutants fail to compile, but over the course of the whole run, almost 60% of the mutants actually run and pass all the tests and produce an interpreter which is actually faster than the original human written code. If we take the best in the last generation, typically this is a bloated individual. In other words, the grammar contains changes which have no impact. And what we're going to do is to use the compiler assembler code as a means of deciding whether a change makes an impact or not. So what we do is we start with the first change of our 16 and we exclude it from the mutant and compile it again. If that excluding it makes no difference to the assembler code, then we conclude that individual change made no difference and we exclude it permanently. So by this process of simply scanning along the mutant through the 16 changes, we reduce it down to just 6, which have an impact. This table just shows the other 3 successful runs where we did this. So in each case, we can reduce the number of evolved mutants down to something quite smaller than the original. Here we have the mutant expressed as a patch. So in red with the less than symbols are the original code, and in green with the greater than is the new code. The first group is the result of three case changes. So these are mutations to the case statement at the beginning of the eval, and you can see it reordered those statements. The second group in the middle, the original code was written using the MM256 instructions, and these are an older type of AVX which allows the CPU to manipulate 8 floating points. And what you see is this mutation has actually drawn in from the Intel library equivalent instructions, but equivalent instructions which operate on 16 floats at a time rather than 8. In this graph, what we've done is we've taken our successful mutant and we've run it on trees of size 3 nodes all the way up to almost 100 million nodes. So these are randomly generated trees of those sizes. We start with the short trees and run through, and each dot gives us the speed up for trees of that size. And then we've run through from beginning to end 100 times, so that for each random tree that gives us 100 data points. And you can see, certainly for the shorter trees, there's quite a scattering of points, and the grey line there plots the average performance. So you can see for trees of about 50 to more than 1,000 nodes, we consistently get a speed up in excess of 20%, whereas for the longer ones the performance is more consistent. There's less scatter, but it's consistently in the region of about 11% speed up. So just to summarize now, what we've done is we've used genetic improvement on our own code. We've shown that genetic improvement can speed up what was the fastest GP system up to a factor of 2. In the process, we've overturned the established wisdom. So it's established wisdom that the jump table was the efficient way to use the interpreter, but in the case of very large trees, it seems that a switch statement is the way to go. And what we've shown is we can use real runtime even in a very noisy time-sharing environment if we take suitable precautions. The last point is obviously a polemic. I mean, if you mutate the code at random, you may break it. But if you're prepared to try multiple times, if you're prepared to have a population of mutants, if you're prepared to put mutants on top of mutants, to cross over mutants, then you too can evolve great things. Thank you. At that point, I shall stop.